All right, welcome everyone. So I'm gonna drop a link in the chat here. Most of what I'm going to be showing is all contained within this Jupyter book, the tutorials I'm going to be showing. I'm going to start with 20-minute presentation just about AI for climate work that my group has been doing, just to kind of set the stage. And then we'll jump into to the tutorial portion, which will cover some example use cases using small data sets that I've put together. If you don't have a working Python setup, maybe you can pull up Google Colab, or in the background while I'm talking for the next 20 minutes, if you go down to the bottom here and create a Python environment for yourself with PyTorch, these are the libraries that you're going to need to run the tutorials. Most of this stuff is already installed in Colab if you want to use Colab. Google Colab, just a cloud platform. But if you want to run it locally on your laptop, you can just run these commands here from a Anaconda environment. But it might take a few minutes to download Anaconda and set this environment up. So you can do that in the background if you need to. All right. So I am a professor in information and computer sciences, but I've been working closely with atmospheric sciences people here at UH for the last couple of years. So I'm very excited about all the things that AI is doing in climate and weather applications. And there's many, many potential applications. I'm going to talk about some of the things that I've been focusing on, but a big research area, I think, for the next few years is figuring out all the different ways that these AI tools can help climate scientists and weather scientists. So I'm going to be talking about a little bit about weather forecasting, climate forecasting, and the types of models, the modeling applications that my group has been looking at are autoregressive models for these forecasting applications, and downscaling methods, or statistical downscaling, which is analogous to super resolution in the computer science field. And there's some new exciting techniques that are being used for this. Of course, I'm not actually a climate scientist, so please stop me if you have any questions or to complain about anything that I'm saying. This is a workshop. We have a small group, and we can have a discussion. So the way that weather forecasting works is we have government supercomputers that run big simulations of the Earth's atmosphere. So you basically take the Earth's atmosphere, you chunk it up into grid cells, you describe each grid cell in terms of temperature, pressure, wind vectors, and you can use physics to run a simulation of the Earth's atmosphere, days in advance to get a pretty good prediction of weather over the next 14 days is pretty standard with the GFS system. The main problem with this is it's very expensive, and it gets exponentially more expensive as you get higher and higher resolution. And so the computational constraints keep us from having more accurate weather forecasts. And one of the big goals of using machine learning and AI methods is to speed up these forecast simulations by a couple different techniques. One of them is to approximate these simulations using faster machine learning based methods. So this is often called a surrogate model. You can take a big historical weather simulation or reanalysis data. You can train a machine learning model to approximate it with less computation. And then once you have this trained model, you can run that simulation forward using the machine learning model, and it might not be perfectly accurate, but it's much faster to do that than actually run the physics simulation. If you're training on reanalysis data, people have showed that it could actually be not only faster, but more accurate, because your machine learning model can actually correct for some of the mistakes that are made in this coarse-grained physics simulation. Another method that I'm going to be talking about is super resolution, which is known as statistical downscaling, or this is the idea that, given some coarse-grained simulation, we can predict what's happening at a higher resolution using statistical methods. And then I won't talk about this, but there's assimilation is the process of combining these simulations of the Earth's atmosphere with observational data, either from satellites or ground stations, and intelligently combining that information, updating your simulations and your model of the world based on these observations. And, that's a statistical problem. Machine learning can definitely help there. So I'm going to be mainly talking about autoregressive models versus downscaled forecasts. These are the two applications that my group has been focusing on. And the idea is, in an autoregressive surrogate model, we take in some data. So this is a gridded satellite data product. We can take in the last half hour of cloud cover, say, and we can use a machine learning model to predict what's going to happen in the future. And basically, we're relying on the machine learning model to learn the dynamics of clouds rather than relying on a physics simulation to do this. In the downscaling setup, we have some coarse-grained resolution simulation, such as the GFS, or Global Forecasting System, and we downscale that to some high-resolution data, such as the satellite data. And if we have both the coarse resolution simulation and the high-resolution data, we can train a statistical model to map one to the other. So a note about this autoregressive model that I'm talking about for the surrogate model, this is completely analogous to ChatGPT and large language models. So these language models take in a sequence of text where each word is represented as a vector, a binary vector indicating which word from a dictionary is at that location. And from that sequence, you can learn to predict what the next word is going to be. And that's how these language models work. If you type in a prompt, it takes that prompt and predicts what the next word is going to be, and it does that iteratively to generate a response. So this is a well-known approach to modeling language. Claude Shannon, the famous information theory person, suggested this in his 1948 paper. The big difference now is that we have an internet worth of text that we can train models on, and we have a bunch of new tricks for training statistical models like neural networks. So what I'm suggesting here is, the same idea of training an autoregressive model to predict what comes next in the sequence can be applied to climate and weather data. The data is just much more complicated. So here, we have this discrete data where we're predicting the next word from a set of words. If we're trying to predict the weather, you have a bunch of real values over this large image. Basically, you're doing video prediction, what's going to happen next in the video. And that's much more computationally intensive and more difficult. But it's an approach that we can pursue. So over the last couple of years, this has been a big focus. A lot of the big internet companies that are doing machine learning research have tried their hand at predicting weather and climate using these autoregressive models. Some of these models are from Microsoft, Google, NVIDIA, Baidu, did Pengu Weather, I think. People have shown very good results where you can, in previous, standard weather forecasting, it takes hours to generate a forecast 2 weeks in advance. Using these methods, it takes seconds to generate a forecast. And what that means is that you can generate many, many of these forecasts using different initial conditions to do an ensemble prediction and get better estimates of the uncertainty in your predictions, that sort of thing. So I guess the biggest challenge is, in all these machine learning methods, the biggest gains have come from really big data sets. So these language models work because you can train on the entire internet, all of Wikipedia, all of Reddit, and you can really pull a lot of information into these models. Weather and climate models, despite the width of the data, where we have lots of data points, in the spatial dimensions, we have fewer time steps in these models. And if you're trying to do forecasting, you really need lots of time steps to learn the relationship of how these variables evolve over time. The easiest gains have come from short-term prediction, like weather or on satellite data, where you have new images every minute or a couple minutes. For climate, it's a little harder because the amount of historical data we have is much less. And so you're really limited in these applications by the amount of data that you have. But we do have lots of exciting new data sources that make this sort of work very exciting. So these are some images from the GOES satellite that my group works a lot with. It provides, each of these satellites provides whole disk images every 10 minutes. These are geostationary satellites. Over Hawaii, we have about 0.5 kilometer resolution for some of these bands, which allows us to do cloud tracking and forecasting. So here's an example of a project that my group has been working on for the last few years. We can train a neural network model that takes in cloud cover maps for the last half hour or hour, and then predict 30 minutes in advance. This allows us to do solar radiance forecasting. This has applications for predicting the net load on the energy grid, which is very important in Hawaii. So this is the kind of forecast that we get. Here's a video of what the clouds are actually doing. Here's the type of prediction we get using a simple neural network model, predicting 30 minutes in advance. You can kind of see that it's blurry, and that's because the model is uncertain. This is a very random stochastic system. You should be a little wary if someone is able to predict with absolute certainty where the clouds are going to be. But this is, definitely better than random. And you can see if you live in Hawaii along the mountains, it's pretty obvious that you're going to have dense clouds caught up along the mountains. One of the problems we run into when we do this is if you want to predict into the future, the performance degrades really quickly. So in this case, if you take the output of your prediction and then you plug it back in to your model, you tend to regress towards the mean and all the clouds kind of wash out in this case. And this is a problem that you have with machine learning systems that are statistical compared to NWP models that follow some physics rules, and they're not regressing towards the mean in the same way. So this is kind of a qualitative difference between machine learning and physics-based computational models. So one of the ways to address this is to combine the numerical weather forecasts with statistical downscaling methods. So in this approach, we use GFS to forecast 2 weeks in advance, and then we use a statistical model to predict from the coarse resolution forecasts what the high resolution cloud cover is going to look like. And so, the GFS forecasts don't really know about the mountains here in Hawaii. Each grid cell takes up most of the island. And so this statistical downscaling actually really works well for Hawaii because the statistical model can capture a lot of the patterns and microclimates that are not captured in the GFS numerical weather forecasts. So my group started a little company that does this, and we've been exploring this and trying to sell it to energy companies. We've competed in a few forecasting competitions run by the Department of Energy, and we always do the best in Hawaii because we're used to dealing with the uncertainty in the clouds, and we're really good at this downscaling stuff. But we tend to not do as well on the mainland sites in these competitions. So this plot here shows day ahead forecasts, and the distribution here is the uncertainty in the forecast. So if it's all spread out, then that means we're very uncertain about how much solar irradiance you'll see that day. All right, so all the same stuff that we just talked about for weather, you can apply to climate. Climate's a little bit harder because you have much more coarser grained climate simulations. So GCM is the equivalent of the weather models. And in these GCMs, they tend to be much coarser grained. So each island is kind of captured in one of these grid cells. But we can do the same thing, and we can try to map what's happening in the atmosphere in this grid cell to what's happening at each location on the islands. So my group has been developing these methods. Traditionally you use linear regression, linear models to do downscaling for particular sites. And then you can do some spatial interpolation using Gaussian processes, which is known as kriging in geostatistics. So you can predict these future rainfall maps by taking a GCM, doing downscaling, doing the spatial interpolation, and then you get these maps. Our group has been exploring deep learning methods for doing this. So instead of this two-step process, which kind of compounds the uncertainty, we just have one big neural network which predicts for any site based on the orography at that site. So it's kind of combining the spatial interpolation and the downscaling in one big thing. So we get maps like this. They have much finer grain resolution than the traditional method, which is kind of blobby. The best example here is on Molokai, where you only have a few locations where you're actually collecting data, but the neural network is predicting a lot of detail in between the sites where you have data. And that's because the neural network knows about the orography, and it's making inferences about how the orography affects the amount of rainfall. So this is predicting the monthly average rainfall across Hawaii at different times. And we can, this is for 2000, this is for the evaluation, but we can make predictions at, 2,100 January using a GCM. This is, again, just showing the kind of detail that we get with our method. So the last thing I want to say before we get started on the tutorial portion is everything I've talked about so far is just mainly using convolutional neural networks and deep learning, but the methods we're using are not particularly probabilistic, and you have this problem that I described of, like, if you're predicting something statistically, you tend to regress towards the mean, and so all the images that you're predicting tend to be kind of blurry. But there's these new methods from generative AI that allow us to sample from high dimensional distributions. And so I'm very excited about the applications of this. I'm going to skip this. So, one of the main application for this is generating AI images. So you can go on to Midjourney, you can type the cat in a hat eating a burrito, and it will generate an arbitrary number of images of cats in hats eating burritos. And you'll never get the same image twice. It'll just keep generating these things. So what it's doing is it's sampling from the space of all images of cats in hats eating burritos. And that's a very large space, right? So what we want to do is do the same thing for weather. Like in numerical weather forecasting, you kind of tweak the input and then you run this ensemble of forecasts to understand the distribution of possible outcomes. These image generating models allow us to do that in a new way that hasn't really been done before. Of course, you have to be careful. So this is an example. This is from a Nature article where people are using these techniques for microscopy. So you have a blurry image of a microscope and you want to use deep learning to do super resolution. But if the neural network is trained on cells, it's learned the statistical properties of cells, and then if you apply it to some input that it's never seen before, like this cat, it thinks it's a cell. If you then plug this into the latest versions of these AI image generators, you can get really, highly detailed cat cell images. But obviously, these are not particularly useful for science. So the way we're using this is we can do super resolution. So we can take this, coarse resolution GFS forecast, and we can apply these diffusion models to generate samples of cloud cover. So here's an example of, the diffusion model is this iterative process which gradually refines the cloud cover image. So it's all grayscale. And when we do that, we can actually generate, thousands or tens of thousands of different cloud cover patterns that could result from the same input. And that's much faster than running 1,000 or 10,000 simulations on a supercomputer. So we've been exploring this method in our latest paper. So the way this works is, we have this UNet. We're using what's called a diffusion model, which is the most popular form of AI image generator these days. And we can generate a bunch of samples. We can look at the mean sample and compare that to, reanalysis data. And, the mean sample is a little blurry, but it captures all the local statistics, such as the clouds aggregating over the mountains. We're also using this for other variables with Giuseppe Torri and Alaric Krenz. So in this work, we're taking reanalysis data and then we're training to predict a really high resolution WRF simulation. So instead of using satellite data for the high resolution data, we're using another high resolution WRF. But once we train this diffusion model, we're able to apply it to any GFS forecast. So we can downscale the forecast for 2 weeks from now. And in this simulation, we're not just predicting cloud cover, we're predicting wind, humidity, temperature, all the interesting atmospheric variables that we need. So here's the input from ERA 5 reanalysis data, the downscaled WRF that we're using for training. Here's a sample at the same resolution as the high resolution WRF. And then the mean posterior is an average over a whole bunch of these samples. All right, so that concludes the overview of this workshop. Of course, this is a non-exhaustive description of all the applications of AI for climate and weather, but that's the kind of stuff that my group is focusing on. So now I want to shift over to this website. I'm going to post it in the chat again in case anyone didn't get it. So this Jupyter book website contains everything that we're going to go through. The different sections, each of these is a Jupyter notebook that kind of stands alone. And it kind of focuses on a different aspect of using deep learning for modeling climate data. The data we're going to be focusing on comes from NOAA's sea surface temperature data. This just seemed like a nice example for this workshop. I've already downloaded and pre-processed the data, so you don't have to download the raw data that we're going to be working with, but I've provided code to do that under this process data section. Do we have any questions before we get started?
I have one question.
Yes, please.
Also, yeah, so maybe more than one, but one at a time. So you generate the equivalent of these ensembles, but they're generated quickly. And you get that by tweaking the initial conditions, or
I'm sorry, did you say Goodreads, or what did you say? What are you trying to do? I didn't understand. I didn't.
Peter, let me deal with the situation here. Okay, I'm back. Okay. So the question is, how are these pseudo ensembles generated, basically? What creates a variability? Are there random components? Do you have to choose some way of scaling the initial condition variation? I'm not quite sure there.
Yeah, great question. So in these machine learning image generating models, the randomness comes from what's essentially a random seed. You're sampling from some random distribution, like a Gaussian distribution. And it could even be a univariate Gaussian distribution. So just a single number that goes into this neural network, and the output of the neural network is a full-blown image.
Okay, but then you have to choose the let's say it's a Gaussian with some mean, which is somehow determined by the mean of the model. But then you have to choose a scale for the random component. And are the outputs, is the variability of the outputs sensitive to the scale of the random noise you're choosing?
Yes. And typically that's fixed at at initialization. So you train, and you fix that variability throughout training and the entire lifetime of the model. But in theory,
is it a user choice?
It's a hyperparameter of the model. So that means, yes, it's a user choice, but the user doesn't really have an intuition for what's good. It's kind of a fixed thing that shouldn't really matter in the end.
No, that was my question. That was my question. Yeah. So it would seem to me intuitively that whatever your scale you choose for the random components will affect the variability of the outputs, but maybe not.
It shouldn't. In a perfect world, it shouldn't matter because you would have unlimited data and the model would learn the variability of the data. But in practice, it does kind of matter because the model will be biased towards high variability or low variability. And a lot of little details affect that, but it's hard to actually know. So in practice, you don't have to worry about it. You just have to worry about training your model and having enough data. All right. Thanks for the question. Any other questions? Again, we do have time, so please feel free to chime in. It's always better if these things are interactive. So the first article here I have is not actually climate data. It's just the toy example that's always used for deep learning, which is digit classification. So I'm providing this because it's super intuitive and super easy. So I'm going to go through it pretty quickly. And if you don't have a working Python installation, maybe you can use this as a chance to get going. So if you click on this link here, this should open up something in Colab. Up here, this means that I'm connected to cloud compute resources. You can switch the runtime to a GPU if you want. You don't really need it for this simple example, but that's something you can do. And this all should run. You can actually just go up to runtime and run all. This is just saying that Google doesn't know who authored this. So I believe this should all just work, and then we can analyze the results. So this data set, let's see. So we're importing Torch, PyTorch, these libraries. Here we're just printing out whether we're using a CPU or an accelerator device. The data set is actually included in Torch because it's a very common data set. So we can just pull up the data set from here. It downloads it. The data set consists of 70,000 little handwritten digits in the form of simple 28 by 28 pixel images. So we're splitting the data into a training set and a test set. So the test set is reserved for evaluating the model. Here we're plotting some of the images that we're going to use in the training set. Again, they're grayscale. They can be a little noisy. So this one here, it's kind of difficult to see whether it's a 9 or a 7. In PyTorch, so whenever you're doing deep learning applications, a lot of the work goes into preparing the data and engineering the data flow so that you can efficiently train these neural networks. So the goal is to take your examples and present them to the neural network repeatedly, and then tune the parameters of the model with gradient descent. That's a lot of moving data around on the computer. So PyTorch has a lot of nice tools for helping you manage all that data that needs to be shuffled around. So I'm creating a train data loader and a test data loader, and these data loaders are iterators. So you can say, data loader, give me a batch of data, and it'll give you a set of images and the corresponding labels so that you can present them to your neural network. So a lot goes into these data loaders, and whenever you're working with a machine learning application, especially in climate science where you have really big data sets, the data loader is usually most of the work, like 50% of the work just to get started. So once you have your data loader set up, we can define a simple neural network. So here we're saying, we have multiple convolution layers. This is called a pooling layer. These linear layers are fully connected layers in the neural network. And we define, so this defines the parameters of this parameterized model. This defines how data flows through that model. This is a textual representation of the structure of the model. I'm happy to talk about any of these things if people are interested. So when the model makes a prediction, that prediction is a probability distribution, a categorical probability distribution over the different categories. Here the categories are just the digits 0 through 9. And we define a loss function as how much to penalize that prediction based on the true label. And this cross entropy loss is a probabilistic loss. Basically, we're trying to maximize the probability of that's assigned to the correct class. And then we're using stochastic gradient descent, but this atom optimizer has some momentum term that helps quickly explore the parameter space. So once we have that, we can run the training loop. So one epoch means one pass through the data set, the training data set. Here we're using 10 epochs, so the model only sees each example 10 times, which helps prevent overfitting. So we have this outer loop over the training set, this inner loop over the examples within the training set. At each step, we make a prediction of the model. We compute the loss function, which compares the prediction versus the target. And we take a step down the gradient to improve the parameters of the model. And then each iteration here, we're printing the loss of the latest batch. And so you should be able to see when you run this that the loss decreases over time and it eventually settles out. So, taking these numbers and plotting them, we see that the loss decreases over time. And if we plotted the accuracy, which is just whether or not we're getting the right answer, we would see that it increases from about 0.1, which is like the chance of random guessing, up to maybe 90, 93 or so. All right. So if we can go through the test set now. So this is all on the training set, but whenever you're training neural networks, we don't care about the training set other than for debugging purposes. We only care if the model can generalize to new data. So we always have to evaluate the data on clean test data that we didn't use for training. So in Torch, we can tell the model that we're not interested in computing the gradients. So we use this no grad wrapper. We iterate over the test set to make predictions. We can store all the predictions in a big Numpy array. We can compute the accuracy, which is actually 99%. That's pretty good. And the test loss is 2.1% here. Or no, this isn't a percentage. So you would compare this test loss to the loss here, and it's actually much higher. I think there's a scale factor that's missing here. But we also expect it to be higher because the model fit to the training data. And we expect it to always be higher on some new data. And whenever you train a neural network, it's always super useful to examine the predictions, especially the ones that you got wrong. So here, we're plotting some that we predicted correctly. And then down below, I'm plotting some that we predicted incorrectly. And it's useful to look at what we predicted versus what the true class label is supposed to be. So here we're predicting 0 when the class is supposed to be 6. That kind of makes sense. This is a poorly drawn 6. Here we predicted 5 and the class is 9. Another 5 versus 9. This is a 9 versus 4. Basically, these all make sense. These are things that you could imagine a human misclassifying as well. But it gets all these correct. All right, any questions on that? Basically, if you look up any tutorial on deep learning, this is always the first toy example because it works nicely and the data set is very small and easy to work with. So I'm going to close this.
Peter, just a quick question. So the test set, how is the test set obtained? Is it just is it a random selection of all the data, or is it done some other way?
Great question. So this test set is all the data goes into a pot, and we randomly select. I think it's 10,000 examples out of that set.
So in a way, that's kind of an easy test set, because if it's randomly drawn, it'll have the same, so at least statistically, same characteristics as the training data.
Right. And when we're working with climate, weather applications, so you always want your test set to be representative of what you want to use the model for. There's the idea of data set drift, where if you're using your model on some different distribution, we expect the performance to drop off. In this case, we really don't have any guarantees on the performance. In statistics, sometimes you have performance guarantees on different data drift. But for these deep learning methods, we generally don't have any performance guarantees. Everything is empirical, and you really want your test set to be representative of what you want to use the data for. So a common problem in climate is if you train a model on historical data, is that model going to work in the future where the data is all different and the relationships of the variables are different? We don't know. There's no guarantees of that. So we kind of have to make these assumptions that we're going to be able to generalize. The things that we can do are evaluate our model on drifting data sets. So, the thing we do in our group is if we have, historical days and we're predicting cloud cover a day in advance, solar radiance a day in advance, we train on a few years worth of data, historical data, and then we use the next year to test the model so that there's a shift in the data. Our test set is totally distinct from the training data. If you just take all the data and then you shuffle it all and then select certain days to be in your training and certain days to your test, you're not evaluating the ability to generalize to drift.
Right. That's much more realistic, right? To use things that are sort of in the future that are not known. It's like getting, with the digits example, it's like breaking in new people to draw digits that,
Yeah, exactly.
that you haven't seen before. Yeah, okay. Thank you.
And that's always a choice. Like you might do different experiments with different data drift based on what you want to use the model for. So that's always kind of a choice, and it'll affect how you train the model, because whenever you train a neural network, you have all these choices for how much you regularize. There's a bunch of design choices in the neural network, and if you want to protect yourself against a lot of drift, you'll be more aggressive about the regularization. So it's very important, and that's always something to keep in mind.
Can I ask something on the training of the model as well?
Yes, please.
So I'm a bit confused with the epochs, because we have one training data set, and then we are running 10 times basically the model by splitting batches for each epoch. Why
Yep.
why do we do this?
Yeah, great question. So there's so the epoch is just a term that machine learning people came up with to mean one pass through the data set.
So does each epoch go through the training data set, the whole training data set each time?
Yes.
Okay.
So we could, you don't have to do it this way. This is a convenient way to, so in gradient descent, we could pass the entire training data set through the model, get predictions for all 60,000 images,
Mhm.
and then compute the loss, and then update the model parameters. The problem with that is it's a lot of computation for one update.
Right.
And so we use stochastic gradient descent. Stochastic gradient descent means you take one example, make a prediction, compute the loss, update the parameters. The problem with that is that it's actually pretty slow to, make a prediction, update the weights, make a prediction, update the weights. You have to do that 60,000 times. And you don't take advantage of the parallelism that is afforded with GPU processors. So the solution is to batch your data. So here we have a batch size of, let's see, it's probably like 100 or something, 64, yeah. So we're actually taking 64 images, putting it in a big data matrix, making a prediction for all 64 images, and that's actually about the same time, wall clock time, as a single image, because a GPU processor can do all these things in parallel. And then we get a loss for those 64 images, we update all the parameters, and then we move on to the next batch. So this mini batch gradient descent is a really effective way of training neural networks,
I see.
as opposed to single training example stochastic or full batch gradient descent where we update based on the whole data set.
Right, thank you.
Yeah, so that becomes important. That's an important part of if you're training like a climate model, you know, engineering how to do that batching efficiently is one of the hardest parts of it, like building one of these systems for climate modeling. And you kind of have to think like a computer scientist and an engineer to figure out, okay, what is the memory on my GPU? How big of a batch can I fit on the processor? That sort of thing.
Are usually the batches the same size and for every epoch, or could it vary as well?
They could vary. Typically, they're typically the same size. There's not making them different sizes would be confusing.
Right.
Because the bigger the batch size, the less variance you have in the gradients. And the variance in the gradients affects how big the learning rate step is. And so you're trying to balance all these things at once. And if you're changing the batch size, that just makes everything harder. So.
Right.
All right. So let's move on to an actual climate application. So this is actually a tutorial that Gerardo Tello gave last year, and I adapted his tutorial for this. This is a project that he works on where he takes sea surface temperature anomaly maps and predicts whether El Nino is going to happen. So it's a classification task with image data, which generally means convolution neural networks are appropriate. We're using all the same libraries. I'll run this on Colab. I think this should be fine if I just run everything. The data is, oh yeah, so the data is already processed. Let's see. So I think this should automatically download the data from, you know, the data is small enough, it's only like 20 megabytes. So I put it in the GitHub. And yeah, it'll just, when it runs this cell, it'll just show up here. Oop. It's complaining. Let's see. Okay, so it is complaining. The solution will be to, if you click on this link, the data should be here. And you can just download this. Yeah. It should be fast because I heavily process data. No. Okay, so I had trouble with this one. It's trying to download a page rather than the raw data. So the solution is to go, if you go to the CSV file and then you click raw here, this gives you the raw data. So you want the raw data and not the HTML. Okay, so then I'm going to upload the data to the data folder here. then it's just warning me. Oh, so another solution is I saved all the data to, if you go ahead to, let's see. Oh yeah, the predicting SST, if you go to this, this drive link, all the data files are here. Okay, so I have these 3 data files uploaded to the cloud with my notebook. So I'm going to put that away. All the files are here. Now I'm going to load the data into what? So it's complaining that I don't have netcdf installed. So what I can do here is so this exclamation point gives me access to the terminal in this cloud environment. And so I can actually install the library right here. Don't know what's happening here though. Weird. All right, so unless somebody has a quick suggestion for knowing how to solve that, I'm gonna actually just punt and run this on my local machine. I don't know why it's doing this to me. Thank you, AI, for telling me what to do. Yeah, I'm not sure why it's doing this. Yeah, I'm sorry. I am a little confused why it's not able to do this. Okay, so I'm gonna go to this, and if someone has a suggestion, let me know. But this should show everything, including the output. So the data processing actually comes from this next thing here. Here I'm loading the netcdf file into an xarray, which is a Python package for dealing with arrays like netcdf. The labels are basically, each time step is labeled as neutral, El Nino, or La Nina. And so the model we're doing is going to take in a date and then 3 images of sea surface temperature, or it's taking in a map of sea surface temperature and then predicting in the next 3 time steps, which are months, whether or not each month is going to be considered neutral, El Nino, or La Nina. So it's essentially, a classification problem where we predict a month in advance, are we going to have El Nino next month? So you should see the parallels to the digit classification, and we can use all the same techniques. Here I'm discussing the importance of splitting the training set into different time periods. There's this term chrono cross-validation. Cross-validation refers to having a training set and a test set. And if you have a time series data, you want to split the data based on some time point so that you can show that you generalized to new time domains. So we're using a batch size of 32, and then this shuffle parameter is quite useful. This means the ordering of the examples in the training set are randomized. We don't need to randomize for the test set, but they should be randomized for the training set. That helps the optimization process work. So here we're defining a neural network model. This is very similar to the model that we used for the digits. The only difference is the inputs here are bigger than the image we had for the digits. If we plot the training loss, the data set's much smaller, so this actually goes really fast, and we can do 60 epochs in just a minute, even without a GPU. But you should see that the training loss decreases pretty quickly. It's pretty common if the training loss jumps around and sometimes increases. That's just noise in the stochastic optimization process. So if it's jumping around too much, typically what you would do is decrease the learning rate. So here we're evaluating the model. We get about 70% accuracy if we're predicting 1 month into the future, and then that degrades the farther into the future we're looking. So at 2 months we have 66, at 3 months we have 61. And then we can take this and do a forecast for more recent data that was not used for training. And we can get a plot. I guess there's nothing to really see, but when this workshop was initially given in December 2023, we could make predictions for what was going to happen in the next couple of months. All right, so that should be pretty straightforward. Next, I'm going to skip ahead to this data processing tutorial. Just shows you how to download the data from NOAA and all the data that's used in these other worksheets. But what I really want to talk about is the problems that come up when doing regression with neural networks. And so I'm going to give an example of how we can use neural networks for regression to predict real values, because we often want to do this in science. And it's a lot more difficult than classification. We can use all the same tools, but the optimization tends to be a little harder. And then from there, I'm going to jump into using these ideas to predict sea surface temperature in this autoregressive model that we talked about. So let's see, I'm going to download this and try to run it on Colab. Actually, it's not right here. Oh yeah, first of all, I can show this. So this TensorFlow Playground is a pretty nice example, or it's a no-code way of getting an intuition for how neural network classification and regression works. But you can initialize the neural network with randomly initialized weights. Here I'm saying this is a regression problem, and I can adjust the learning rate, and so it should learn, you can use this to visualize what the neurons are learning. Each of these colors corresponds to the strength of the weight between the network, or the neurons. This is shows the prediction. So each point here is a training point, and the color indicates the value. So this is a two-dimensional input. Test loss and training loss are up here. You can see that they diverge. You're overfitting a little bit, so the training loss keeps going down, but the test loss is still kind of going up. And you can adjust the amount of noise and the batch size to see how this affects the optimization. Okay, I'm still having trouble with actually running this, so I'm going to go back to this here. So in this, I'm generating some synthetic data just to demonstrate a point. So the input is one-dimensional, the output is one-dimensional, and this is a heteroscedastic regression problem where the variance of the output changes over time, or changes with the input. But this is a nonlinear relationship, and so you typically would not want to rely on linear regression for this sort of task. And you might want to use a neural network. So I've plotted the true mean and the true standard deviation here under the synthetic data that I made up. And we're going to train a neural network to try and predict the mean and the standard deviation. So the neural network is going to have two outputs. The first is going to predict the mean. The second is going to predict the standard deviation. And so this is a probabilistic model of the data. It's actually telling you how uncertain you are about this output. So I'm defining a heteroscedastic neural network here. And again, the important parts, it has two output. It's predicting the mean and the standard deviation. And then the loss function is going to take into account both of those values. So if the model predicts that it's very certain about the output and it's wrong, then it has a very high loss. And we can think about this probabilistically. We're trying to maximize the probability of the target Y given the input X, where from X, the model predicts the mean and the standard deviation. So, just as before, we can train the model using all the same tools. We can see that the loss decreases, but it hasn't really decreased too far. If we trained longer, I would expect it to fit the data much better. So here in red, we're predicting the mean and the standard deviation. And the model hasn't really fit this upper curve, right? It's kind of ignoring this downward slope. But it does show up in the standard deviation, like the model becomes less certain over here. So here's a diagram of what this looks like. This is a neural network design strategy for probabilistic modeling, where you have one arm of the network predicts the mean, one arm predicts the standard deviation, and the loss is just the probability density at the target. But this is extremely flexible, and you can use other distributions. You can use other architectures. The input here is just one real valued scalar, but the output could be, or the input could be an image. And this is super useful for science applications. But it does require a little bit more, modeler design to get something that captures your intuition about the data. It's also more difficult to optimize. In a classification problem, it's, you just have to predict the right class, but for regression problems, you have to predict, the value without going over the value, and that tends to lead to much shakier training. So from this is just a one-dimensional case, but often we have multiple output values. So in weather forecasting, we want to predict multiple types of values, temperature, precipitation, humidity, but also at different spatial locations. And so the output is actually, often thousands of variables at once. And if we use this strategy, where we have multiple outputs of our neural network, that can work, but we also run into this problem where each of these outputs is considered independent in the modeling. And what we really want to do is model the joint distribution over all these variables, and we need even more complicated models for that. So what I'm going to do now is show you how to take this strategy where we're not doing anything complicated like diffusion models, but we are predicting real valued outputs for sea surface temperature, and we're predicting multiple outputs at once. So we're using the autoregressive technique. So in this article, we have our data set. The data set's actually coming from this up here. And this is a monthly sea surface temperature map since 1854, all the way up to 2025. And you can see that here, the data set loader, I mentioned that this is usually most of the work. It's gotten significantly more complicated. And the reason it's complicated is because we want to take multiple time steps of sea surface temperature maps in order to predict what's going to happen in the next month. So here I've set the sequence length to be 3, where I'm taking 3 months of data, and then I'm going to try and predict what happens in the next month. So again, I'm leaning heavily on this the PyTorch tools for managing all this data. And this is just showing one batch of data that I'm going to feed to the neural network. It has a batch size of 4. So I have 4 different time steps. Each time step contains 2 maps, and then 41 grid cells of latitude, 86 grid cells of longitude. So basically 2 images, and then the output is 1 image. So I'm taking 2 months and predicting what happens in the next month. And then I have 4 examples at a time, so I can train in parallel. So here's a simple autoregressive model. The model itself is actually pretty simple. It's just another convolutional neural network. Here's the training loop. I'm going to train for just 5 epochs, 5 passes through the training set. And I can see that the loss goes down, but it really hasn't decreased very much. So you really need to work with the data and play around with these learning parameters. So given this, it seems pretty stable, but I would increase the learning rate to make it train faster, and I would train longer. So once I train the model a little bit, I can I can take one of these, data frames, or from the data set, I can take a set of 2 sea surface temperature, at adjacent time steps, and then I can run it through the model to make a prediction. So here's the prediction, and it's predicting 0 almost everywhere, and presumably this is because it hasn't actually learned much. I haven't actually had time to train it very much, and so the results are not good. But I would expect it to actually learn some patterns. Eventually it would just overfit if you train it long enough. But those are all the pieces to do an autoregressive model on these climate surrogate models.
Well, Peter, can I ask you, the autoregressive model, is that predicting the next month's sea surface temperature map all at once?
Yes.
But is it doing it pixel-wise somehow, or is the autoregressive model somehow both in space and time?
It's making all the predictions at once. I'm not sure what you mean by space and time. So it's just predicting the next month's sea surface temperature anomaly.
Okay, just wondering whether the spatial variation is treated with some type of model. That is, that the sea surface temperature here is autoregressively related to, or moving average related to, sea surface temperature around me.
Yeah, so I'm not sure I understand your question. So it's, each pixel here, it's not showing the pixels, but each pixel is treated independently, like the air. So it won't necessarily pick up on the spatial correlations between 2 adjacent.
Oh, that was actually my question, whether there's a different autoregressive model for each pixel, or whether somehow it's done simultaneously.
Yeah, so it's done. Yeah, so what's the language is, it's not modeling the joint distribution. So it's going to be pretty blurry. I think, the way to, this is kind of the cartoon image that you should have in your head. this is an autoregressive model on satellite data. You know, the real satellite images are nice and crisp, with very high spatial correlation. And when you make a prediction, it tends to blur everything out because each of these cells is, the air is treated independently. There's no joint distribution. In order to capture that joint distribution, you need something like these image generating models, or this example, where you're actually capturing that spatial correlation when you generate samples. But so in this case, here's 5 samples from this high dimensional probability distribution. If we take the mean of a bunch of those samples, we end up with something blurry. And so what we're doing in this example that I just showed is predicting this blurry thing, not predicting these nice crisp samples.
Okay, got it. Thanks, Peter.
Tiziana, did you have a question?
No, thank you, Peter. Actually, you answered the question while you answered the previous question, so thank you.
Okay. Yeah, so, I think what do I want to say? I want to highlight that, in this, when we do this is kind of a researching thing, but typically people make the blurry images first, and then you actually use this diffusion model to model the residuals around that. So in this application, we're actually predicting this mean first, and then we're adding the diffusion on top of that to model the variance and the relationship between the adjacent spatial points. And it's a very common thing to do. I don't know if it's the best thing to do. It's kind of an open research question. But that's the most common thing, because you have this mean prediction when you want it, and then if you want to sample the variability and find these correlations, you can get that as well. Okay. So that's pretty much it. I'm happy to answer any other questions. I'm sorry that I had a bug with the X array. I think it's just something simple. The X array on Colab doesn't know how to process these netcdf files. But maybe I'm just doing something silly. I'll try to fix that and fix this website soon. Please fill out the survey if you get a chance. And otherwise, I'm happy to answer questions with the time we have left. Thank you very much.
Thank you, Peter. Matthew here. I had a couple questions.
Yeah.
The first one, the SST prediction. How does that compare to a long short-term memory model? Is that the same?
No, it's not the same. Although it's probably not very different. So a long short-term memory is a particular neural network architecture. This is like a 1D convolution. You're basically convolving over time, and you're only taking the last 2 time steps and predicting the next time step. A recurrent neural network, like a long short-term memory network, LSTM, allows you to incorporate all the historical context, however many time steps you have in the past, to help make that future prediction. Um, it allows you to incorporate more information, but it also leads to overfitting because you have more information that might, you don't want to include information into the input of a neural network that's, isn't going to be useful because it'll just distract you from finding the patterns that you care about. So a long short-term memory network, the innovation there is it allows you to take in an arbitrarily long history and the LSTM part, as opposed to a standard recurrent neural network, allows you to kind of find nuggets of information far back. The attention mechanism in transformers basically does the same thing. As an LSTM, it allows you to retrieve information from something that happened long ago in the sequence to help make your prediction. That's, for a lot of climate applications, I think that's overpowered. People love using them because they're cool and they're easy to use, and there's lots of examples out there. But I think for a lot of these things, you're just going to overfit before you find useful information. So I always like to start with something simple where I just look at the last couple time steps and assume that what happened last year isn't going to be useful in making a prediction for tomorrow or next month.
Thanks. That was really helpful. Helpful for me. Just the second question, just a much more general question. For a group just getting started with this kind of stuff, do you have an opinion, PyTorch versus TensorFlow?
I would say PyTorch, but Keras is really nice for simple things. But I think I would recommend PyTorch. But I like giving tutorials in Keras because it's so easy to do things. But the problem is once you step out of really basic things, you start running into problems. And PyTorch is much easier for doing. I would say for weather and climate applications, PyTorch is probably better because you have more flexibility. And with climate and weather applications, there's a lot of data engineering that has to go into it.
Okay, thank you.